So, hello everyone. Can you guys hear me? So we proceed. There are a few problems. Some of our friends cannot join the WebEx. Make sure they can watch this video from the YouTube live. So we just start our class. Okay. Anything further about our quiz this Friday? So today we are going into a new subtopic, Newton's method, as you can see. Okay. So some of you might have heard about Newton methods in the past. Do you? Oh. Okay. Yeah, Newton Edison. Yes, specifically. Have you guys Google anything? So actually, Newton methods is something that we call numerical methods. Forget already. It's okay. Forget. It's much better than if you haven't learned about it. So it'll be a new thing. But if you forget, to polish it. Okay, to remove all the rust. Okay. So basically, Newton method is actually a numerical method that is used to find roots or solutions of an equation. But okay, there's a big but there. There's a like argue that this method sometimes is not the best because this kind of method suffer a lot of disadvantages or drawbacks. Okay, whenever we have to choose the initial guess, if our initial guess is incorrect or sometimes the patterns of our functions is different, you to the right route or it will not lead you to the route at all. Okay, so there are a lot more numerical methods that you have like Adam Bashford, you have using Taylor polynomial, you have method, perturbation method, and many more. And Newton method is one of the simplest, and it is almost compulsory for everyone to learn about Newton's method. It is simple and it converges faster whenever applicable. Okay, so there are times that Newton methods are not applicable. Okay, and we have to use other methods. But in this syllabus, since we try to relate the concept of derivatives, so Newton method is the best one. Okay, so if you go to softwares like MATLAB, Mathematica, and so on, most of them started to compute, okay, using Newton's method first. Okay, but if Newton's method fail, they will opt into using another method. We have many more. We have few hundreds methods, and it's still coming in because when we talk about numerical methods, let's say we have one Newton methods, for example. The second one, let's say we have Cups method. So basically, you can do some adjustment and combine them. Okay. Let's say we have one method, and then we have two methods. We have three methods. These are numerical methods, or another. You can actually couple this one and two, couple one and three, and then couple one, two, and three. But the most basic one is Newton. It's very much related to what we have learned previously. Okay, the derivatives. Okay, we have Rolle's theorem, we have intermediate value theorems that all are related to Newton method. Okay, so Newton method are also called Newton-Raphson method, but okay, it has been argued who have introduced this. Sometimes people say this is proposed by, I'm not sure, not Newton and not Raphson else, but Newton, okay, been able to grab that idea and publish it and make it his own. Okay, so again, Newton method is a numerical method and it is used to approximate the solution to an equation x equal to 0. Okay, so can be any kind of equation as long as you can make sure that one, okay, in this case our right hand side is 0. So in this case you have 2x plus 1 equal to 3, still you can bring side and get 0 on the right hand side. Okay, so basically the idea of Newton action is it uses tangent line, or what we learned previously, we also call that slope. Okay, we have a slope and then we use that value of slope to find the tangent lines equation. Okay, we have learned how to find tangent lines from slope. Okay, tangent line, and also we have learned how to use that information of slope to find the normal line. Okay, not going to use normal line here. We are just going to use tangent line and the idea of slope. Okay, so of the graph of y equal to fx near the point is 0 to estimate the solution. So one of the keyword here is near the points. Okay, so if you have some points that from our root and you try to estimate, normally okay, it will be error. But again, the concept of near is right. Okay, maybe I say, let's say I want to I want to travel. I say that Perlis is very near, 2 hours, but maybe some saying that near is very that Perlis is very far, right? So the concept of near here is very subjective, and actually it depends on the trends on graph. So you have to recall again that when learning mathematics, basically everything is about trend. For example, in calculus here, we learn about trend of function. And you go to graph theory, and then you learn trend of graph. And then if you learn algebra, you learn the trend of the unknown, and so on. So mathematics is actually about trend. So when we talk about trend here, we call it near to the points. So it is different to every one of us. But it is depending on the trend of the functions. Okay, we'll see that later. So f is 0 to estimate the solution. So this is we have just now. F is 0 to estimate the solution. So recall again the tangent line. You can see the figure here. Okay, xn, fxn. Then we have slope f prime xn, and then we construct the tangent line equation. So if you still remember sort of y minus fxn, okay, because we have the value for fxn over x equal to f prime xn. So you still remember we have this kind of formula which can also be translated in x plus c and so on. But from this equation, you want to transform it into this equation before we try to formulate it to get the form required for us to perform Newton method or Newton Raphson method. Okay. So taking for example here, we choose xn here. Okay. We know the value of xn, and then we can compute fxn. Okay. And then we try to find the tangent line at this particular point. Okay. So initially we have this one. Okay. And then we compute the tangent, the slope first. And from the slope we construct the tangent line. Okay, which is this one, tangent line equation. Okay, so this is our tangent according to our slope. Okay, and then that tangent line have a y an x axis intercept. So here, so you draw a line here and find out that at here, okay, cross the x axis. So we are going to use this second point as our better estimation, okay, or better guess of the root. Okay, so you guess this one in the first place. To find the slope at our curve here, and then we perform procedure to find the tangent line equation, and then from that equation check the x axis intercept. Okay, here, and then we are going to repeat the same procedure again. But in this figure, it only shows one iteration. Okay, by one iteration, I mean we only perform this formula once. Okay, where does this formula come from? Come from this one. Okay, just a simple manipulation. You bring everything and you only have okay on the one side. Okay, So again, this is the next figure. Okay, just now we have xn plus 1 only. Okay, this is xn, this is xn plus 1. So the thing now we have 1. Okay, this is okay. So from our initial guess, x naught. Okay, we have x naught and fx naught, and from there you find the slope. Okay, and then you construct tangent line equation, and then you find the x-intercept, okay, from the tangent line equation. Okay, and then from that one, okay, if previous figure we have here as xn plus 1, but now instead of labeling as n plus 1, because the first one is labeled as x naught, or x labeled here as x1, and then we are going to repeat the procedure again. We have x1, okay, then we find fx1, then we find this particular point in the curve, okay, and then we construct the tangent line equation again, and then we find the next one. Okay, repeat again and again and again until the value of the root, okay, the approximation of the root satisfy our condition. Okay, the condition here is actually area, the distance between our root. Okay, distance between root. Okay. Root is the point here, the root that you want to find here, and okay, our x lah. In this case, our x cube, x sub 3. Okay. See the first, second, and if you keep performing the Newton's, okay, the iteration, you will get something closer and closer to our root. So again, you can see from this caption here, Newton's method start with an initial guess, okay, okay, yes, and improve the guess one step at a time. But it mentioned here under favorable circumstances. That Newton method does not work every time. Okay, sometimes you choose a wrong initial guess. Okay, will suffer. You find the root, or you will find a different root. Okay, so again, we are human. We see the word guess here. Guess is something that is performed by human. Our judgment. Okay, so when we talk about judgment, human judgment, it is prone to error, right? So you need to perform the right guess in order to find the right root, okay, to approximate the root. So this is the summary of me. So again, the first one is guess, first approximation to a solution. Okay, you can plot the graph. Okay, you have the find. You can plot the graph. Sometimes the graph you cannot see where is the point that the graph exactly cross the edge or the root. Okay, that's why we need approximation. For example, set 2. Can anybody give a perfect value for 2? No, right? 2 is irrational. Okay. If you try to write down the numbers, it goes on forever. Okay. You can keep, but in Newton's method, we are trying to we try to approximate, which means we are trying to find some value very close to the set 2. Okay. So the second step here is we are going to use the first approximation to get the second, to get the third, fourth, fifth, and so on, using the formula. So let's play around with the formula. Okay. So basically, initially we have, okay, what do we have? We have x minus fxn, okay, over xn plus xn, xn plus 1, or x minus xn equal to. So we know all this. Okay. So with some manipulation, you'll get what we have just now. We have equal to xn minus fxn, okay, over f prime x n. Okay, so this is the manipulation you did. So where did fx disappear? Okay, so if you try to do it again, you actually have f prime x. Okay, no problem. Let me write f, and you have x minus xn. Okay, if you bring this up, okay, you have what? You have plus f x n equal fx. So from this until this, okay, you can perform direct manipulation. You bring this one to the right hand side, and then you bring minus fxn to the right hand side as well. And then why don't we have fx here? It's because we consider x intercept, right? And x at x intercept, our our fx is equal to 0. Okay, so we have 0 here, then we have f prime xn, x minus xn plus f xn. Okay. And then using simple manipulation, you bring fxn left hand side. Okay. This here we have plus, then we have minus fxn. Okay. And then you bring f prime xn. Okay. Okay. Because this is multiplication, that's why you have fraction here. Negative fxn over f prime xn. And then what left on here is x. And then you bring xn to the other side, and finally we'll get this form. Just a very simple manipulation. Finally we have this one. So f y disappear because it is equal to 0 when we have the x intercept. Okay, so now towards the application of Newton's method. So it says here find the positive root of the equations. So if you use algebraic manipulation, this example is pretty simple, right? We have minus 2 equal to 0, and this will give you x squared equal to 2, and this will give you x equal to 2. Pretty simple, right? We know the exact solution. So this is something that we call exact. Okay, but approximate the values. Okay, and we are going to use Newton's method. This one. So this example, the example you have to do on your own. Okay, so we have fx equal to x squared minus 2. So recall again our formula. Plus 1 equal to xn minus fxn f prime xn. Okay, f prime xn cannot be 0. So the next thing is we already have fx. So we have fxn equal to x squared minus 2. Okay. Next element in our formula is f prime xn. So we are going to differentiate this. X squared you will get, and then 2 you will get 0, right? So now we are going to plug in everything into our formula. Okay. You check, we have xn plus 1, xn plus 1, okay, is equal to xn. Okay. This is our xn. Okay, and then we have minus fxn. Okay, then we have f prime xn. Okay. We need to perform initial guess. Okay. So initial guess is no trick for initial guess. The only trick available is you draw the graph. Okay. So you can try to draw the graph. Okay. But I'm not going to do that. On your own, I'm going to make my initial guess. Okay. According to the graph, but we don't have the graph here. X naught is equal to. Okay. This is my initial guess. So next we are going to plug in. We have xn plus 1 equal to this xn plus 1. So now our n is 0. So we have only xn, x1. So we have xn or x0 here. We have, then we have minus. Then we have 1 square minus 2 over 2 times 1, 2. And then you get, what's the value? The first one is, can you compute it for me? Because I don't have calculator. I have the values, but I don't want to compute it. We have 1. 1 minus 2 is 1. 1 over 2 is 1.1 plus 1, 1 over 2, or 1 plus 1 over 2 is equal to 1 and half, 1.5. So let me write our exact solution. Okay, 1.414213. Then we have 6237 and so on. Okay, so iteration for me. X2 x1 minus x1 square minus 2 over 2x. What will be the value? Get value? It's very simple, right? Okay. 1.41 and so on. 1.4166 and so on. Yeah, I'm just going to end here. 1.7. Okay. How about the third one? 1.41422 and so on. So you see, we have our first guess is x0 equal to 1. Then we have x1 is 1.5 and x2 is equal to 1.41667. Then we have x3 equal to 41422. Okay, you see the root here or the solution here, the approximate of our solution here, closer and closer to this value, right? We have 1, okay, very far from 1.414 and so on. Then we have 1.5, getting, then we have 1.41667, getting closer. Okay, then we have 1.41422, getting closer and closer. So if we summarize, okay, this is our values. So we have S0, I'm going to write again. We have 1, 1.5, 1.667, and 1.41422. Okay, so if you compute the error between our, we have x0. This one is x0 minus x. Okay, that's it. So you have 1 and then you minus the z, then you get this one. Okay, and so on. Okay, so you have error for this. Okay, when we talk about error, we talk about magnitude. That's why we don't really care about our So actually better to use error as with absolute. So we don't have negative here. Okay. To measure the distance between our exact and our approximation. So this is our first error, and our second error, and then third error, and then so basically we have, okay, the error is getting smaller and smaller. So if you compare between our exact solution, for the first one, okay, only one digit. So the first digit is correct, one here. And then the second one also one, because our second digit is 4, 1.4, right? Okay, we have 1.4. And if you compare, okay, I'm going 1.41421356. Okay, so if you compare our third approximation, okay, we have 667. So 1, 2, 3. Okay, number of correct digit is 3. And then for our last, we have 41422, 4142. Okay, so it means that we have 5. Okay? So if you keep doing x4, x5, and so on, okay, the number of correct digits will increase. Okay, you will get something more and more similar to our exact solution, and the error will become very, very small at one point. Okay, first, okay, they say you want error to be 0.00000000, for example, and then you have to compute until the error fall within this range. Okay. If you don't remember it, maybe by the time now, you already, oh yeah, it was like that lah. You start all the procedures, because Newton methods is very simple but powerful. Okay, given some conditions, favorable circumstances. So for this example, I'm going to give you like 2 minutes to try to the x coordinate of the point where the curve y equal to x cubed minus x cross the horizontal line y equal to 1. Okay. 2 minutes starts now. So check again, cross horizontal line, not cross x axis. The x axis y equal to 0. Previously we have y equal to 0. Okay. So we are not going to use that now. We need to use this. So with just now, we have x cubed minus x. Okay. Because cross x axis. Okay. But now we have cross y equal to 1. So we have x cubed minus x 1. Okay. Before you perform the iteration, you need to know this fact. Okay. So the first thing that you have, sure one of the, okay, in this case right hand side must be 0. So you have, I'm going to write here. So this is our function. Be careful. So I'm going to give you the initial guess. Again equal to 1. So actually x naught can be obtained from figures. You plot the graph here. X cubed minus this one. Okay, then you see this is where the graph cross the x-axis. Okay, because now we consider -1 already inside our function, our equation, but we don't know specifically what is the values here, okay, if we don't use calculator. So we are going to take something to the root. In this case, we want to try to use 1. Okay. You can take 2 and so on, but in this case, my initial guess is 1. Elwin, it depends on our conditions. So the question stated the error, and you must compute until your error fall between that error for a condition for error. It depends on the question. Okay. So we have fx, this one, f prime x equal to 3x squared minus 1. So we have xn plus 2xn, okay, minus, okay, can do. Did you compute one by one or you compute using calculator? If back in my time, I prefer to use calculator. You can directly press calculate or solve rather than, I'm not mistaken. So you just keep doing and okay. But you have to perform that and put it inside the table. It's much easier rather than compute. No, you have to press again every time. But calculator is good. I don't mind. You don't have to show every step. Okay, this is one of the most important step, and then you press repeat and f prime xn, and then everything the value after that you can do that in calculator. Okay, so we have xn minus x cubed minus x minus 1 over 3 x minus 1. So this is where you get marks, huh? In exam or test, this one will give you marks. Okay, but it's there. So in this example, you can see. Okay. I guess you're done, right? Okay, so I can proceed before we discuss about the solution in the slide. So we have here. So just now we start with 1. So if you still remember, we find the 1, -1, and then perform. Okay, this is what behind the Newton's method. You have the tangent line equation, then you find the second, the root here, second approximation x1, and then again you interpolate again. Okay, you find the point on the curve 0.875. Then you are going to construct the tangent line equation, and then you find another point here. Okay, our third guess x2. In this case 1.3478, and then you can go on forever. Okay, so this graphical illustration is decimal places. Okay, so okay, I guess you all are already performed it. I'm going to go through this one. So we have our first guess 1, then you compute fxn negative 1, then you compute f prime xn equal to 2. So you're going to take this value, and this value, and plug in here, here, and here, and then you'll get xn plus 1, which is this one. So that's the first one. And then xn plus 1 will be our guess here, xn. Okay, and then you are going to repeat the procedure, compute f prime xn, and then you take this one, and this one, then you plug in into our formula, and then you get a new value. Okay. So you're going to repeat again and again and again until you get the satisfied. In this case, okay, if you still recall the question here, doesn't state Doesn't state until when we have to do the iteration. Okay, but basically we state our error, or if the question said up to digits, for example. So if error, I think we can do as in the previous one. Okay, we do the iteration until the error within the terminating criterion. Okay, our condition for error, and then if the question stated 10 digits, for example here, this is like 10 decimal places and so on. So two consecutive iteration or approximation, okay, same digit for the first 10 digits. So in this case, we have 1.5 and 1.3. Only two digits, okay? Only one digits agree with each other, which is 1. And then you perform again. And then you check, okay? Digits, we have 1 and 3. 1 and 3. So only two digits. Okay. Next, you perform the third one. So we have 1.32, then 1.32, which means we have 3 digits. Okay, this one means right, 2 digits. This one is 1 digit. From another iteration, we have 1.3247, 18, 1.3247, 17, and you see that 1, 3, 4, 5, 6 digits in agreement. And then you perform again. We have 1.3247, 17957, and it's the same here. Okay, so we have 10 digits in agreement. Okay, but bear in your mind that actually we write until 10 digits here, but in real life it can be more. So if the problem stated 50 digits, you have to compute until you have the same 50 digits in consecutive approximation. Okay, so we have here 10. So you can go so on according to your terminating criterion. On what condition will you terminate your iteration? So far, okay. The essence of this lecture is actually this formula only. You have to know this formula, okay. And you have to know how to compute. In this case, I prefer you all to use calculator. Okay. Problem not having calculator at home? Maybe you left in USM? No. Good. So if you can download into your phone. So now we are going to check the convergence. Okay. So like we discussed earlier, in most cases, okay, you have favorable circumstances, you will get the root very fast. Will converge very fast. For example, in this case, patterns we have for the error, we have 1, 2, 3, 6, 10. You see, from 1 it goes to 2, goes to 3, it's very slow, but then it goes to 6, and then it goes to 10, and maybe after this it goes to 20. It keep getting faster and faster to reach criterion or to have a more favorable results. Okay, more agreement between consecutive results. Okay. But that your guess. So this is one example where Newton's method fails. Okay. Okay. So to be convergent, we must have favorable circumstances. So Newton method fails. Let's say you choose x naught here, and then you find your fx naught. Then you have it, and you get x1. Then you do the same thing. You repeat your procedure. You find your fx1 here, the tangent line, okay, then you find it cross x0 again. So it goes on and on forever. Okay, this is one of the condition situation where Newton's method fails. Okay, you will oscillate between x0 and x1 forever, not getting closer and closer. So this is one kind of function where we cannot use Newton's method. So this is another situation where Newton methods fail. Okay, not some of it not directly fail, but this is we start too far away. We have wrong initial guess. Okay, so is that, for example, we have x naught here. We want to find this root. Okay, not this root. Okay, for example, we are giving the interval between this until this. So you are choosing x naught here, and if you try to, you know, uh, extrapolate or interpolate this point, try to find the new approximation. Okay, you find fx naught here, and then you use a tangent line to find x1. Then we have x1 here. Okay, and then finally we come closer and closer to this root, not the root we want here. Okay. One of the problem when we choose the initial guess too far. Okay. So this is another condition. Okay. So for example, we start with x naught. Okay, we want to find this root. So polate here. Okay, you have x naught, you find fx naught here, and then you find x1 here. Then you find the third guess, okay, or second approximation, and finally you will go closer and closer to this root. So again, this is because our too far. Okay, it falls after the almost closer and closer to the extremum. Okay, normally in test you can plot and then you can find a value very close to our the root. So for example, we have this kind of root, and we have 1, 2 here, maybe 1.5 here. We can choose something very close. 4. Okay, because in our test is a take-home test, so you can bring home your test and any plotting device or online, okay, web to plot your graph and find your initial guess. So I guess that's it until today. The homework will be passed after this class. Okay, so that you have the homework today. You want to prepare for your quiz? Lecture ends until now. So I'm going to stop sharing. If you have question, you can ask me. Okay, so homework and problem set will be given after Friday quiz. Okay, so you can do during your weekend. You have your okay. So actually the homework is pretty simple. Everything again, but it's okay. So again, the problem set. Okay, the problem set 6 solution will be uploaded today so that you can use that maybe to revise for the quiz. And then second thing we have is your homework for, and the new problem set will be given after the quiz. Okay, so again, quiz is on Friday 2:30. If you have any question, you can ask me. So one of our friend asked how to get the initial value. Must be 1? No. That's why actually 1 is intuitive. Okay, which in most cases it gives us wrong. Maybe the guess is too far away. But the right way is to plot the graph first. Okay, you plot the graph, and then you can, you can see at which point our root happen to be. Okay, let me try to draw. I'm going to share again my slide. So okay. initial value. So the first thing is you have to plot the graph. So for example, you have x square minus. So you know that this would happen here, and in your graph you have the values -1, and you know that from the graph the root happen here, so you can choose something around here, maybe -1. So basically, the choice of initial guess depends on your graph, or sometimes in the question it will be given. So normally in final exam, it will give you the initial guess. Okay, but since this time we have take-home test, maybe using software like Desmos, and then from that plot, you have to make your own guess. I will just give you the terminating criterion, maybe 10 digits or maybe using error. Okay, is it okay? Good. If you still have any question, you can ask me. So technically, we finish. Thank you.